Wasn't showing up, so now I have to see.
Maybe that's better if I can, but it's almost like I have to talk down, but I don't want to talk like this the entire time. That seems rough, so I'm gonna have to talk like this. Testing, testing. I hope everybody's enjoying their coffee break. Looks like they are. Is this okay? Do you think this is an okay volume for online?
Online is perfect.
Perfect.
In the room, you're going to go to the back room. You just keep doing your thing.
Okay, sounds good. We have some time, right?
All right, we're going to get started again, everybody. Good to go? What's that? Wonderful. All right, we have our last presentation of the day right now from Kim Wariski. Kim's going to be talking about an introduction to hidden Markov models, which is a really exciting frontier in a lot of animal tracking studies. Hidden Markov models are predominantly used with continuous track data, and Kim's currently doing her PhD in statistics here at Dalhousie with Joanna Mills-Fleming, who we heard from a bit earlier today. Kim and I first met playing soccer at Dalhousie here when we were both undergraduate students. I think that was 2010. So we've known each other for about 10 years now. We've been friends that entire time. We've worked together. We've done a lot of activities together inside and outside of science. And for about 5 years, we've been involved with ideasOTN doing various projects. And this is our most recent one that we've put on. So Kim's a great friend, and we've collaborated on a lot of papers. I think the first paper I ever published, Kim helped me figure out all the stats for. So I'm forever indebted to Kim for her fantastic capabilities and willingness to help others, and I think this workshop is a really great representation of what she's able to do and the way she's able to give back to other scientists in our community. So please help me welcome Kim and thank her very much for giving this awesome introduction.
All right, just let me get situated here. Let's see if this works. Put this in my backpack. Okay, can everybody hear me? I think we're all right. Okay, thank you so much. That was the kindest introduction I think I can ever expect. So today I'm going to be talking to you about hidden Markov models. I've been working with these models for, 3 or 4 years now. I luckily have one other person in my lab who is also working on them or has worked on them before, and so he and I get to discuss a lot about them, and it really helps me learn. Today, the code that we're going to be doing is not actually one of my own R packages, so I'm going to be looking at the MoveHMM package and the MarkMod mover package. Those two packages were written, the first one, MoveHMM, was written by Teo Michelot, second one by Ethan Lawler, who is in my lab, and he's here today, so I may or may not call on you for help if I need it. Both of these people are absolutely fantastic researchers, fantastic statisticians. I had the opportunity of meeting Teo 4 years ago, I think, at one of the ISEC conferences. Really funny, really nice guy, really smart, obviously. Same goes for Ethan. So if you guys have any questions about these packages, I would definitely recommend. You can always ask me, but I'm not the expert. I would definitely recommend asking and getting in touch with one of them. With that, though, I think I can do a decent job of introducing HMMs in general. Maybe, if it works. Do I need to click on? Yeah, I probably need to just. There we go. Okay, so yeah.
Sorry.
I think it's working. I'm already there. It's fine. Or not. I think it's working. Yeah, okay, so the whole point of an HMM, what we're trying to do is when we have I'll talk about this with regards to animal paths, but when we have a path, what we're interested in doing is fitting these, sorry, I wander a lot. We're interested in fitting a model that can uncover some sort of discrete behavioral information about this animal path. So we have this track, and a very classic example is a gray seal foraging behavior. That's what I often work on just because I have the opportunity to go to Sable Island and we have a great program here with a lot of satellite tracking data. This isn't a gray seal example, but if you can picture area restricted search, what we have is a lot of directed movement, and then we have a lot of kind of squiggly lines just in one particular area, right? So we assume that an animal is probably moving in some kind of moving towards an area that they've been before, like a grocery store, right? And then when it's in the grocery store, it's in the foraging patch, it's going to move all around throughout that grocery store, and it's going to find all of the fish that it can possibly eat. And then it's going to move back to a different grocery store and then find more fish that it can eat there, right? And so we're really trying to decompose a track into these two different discrete behavioral states. But it's really important to know, and there's a lot of people who like to talk about this a lot, it's really important to remember that those discrete behavioral states are math. You know, we're coming up with these values that are ones and zeros, or ones and twos, and it's up to us to be able to interpret them correctly. So it's up to us to really be able to inform these models. And I think a big purpose of this talk, and a big point of the coding lectures, is going to be that there are a few subjective choices in hidden Markov models, and it's going to be really important for everybody going forward to make sure that you're documenting your assumptions and documenting your steps along the entire way. And so you'll see this in my code, and that's because my code is mostly comments, okay? And so I suspect we won't even get through most of it today. You are welcome, John. I suspect we mostly won't get through it today, but you'll be able to follow along, hopefully, on your own. And so we have this continuous in-space animal track, and what we're trying to do is get to a continuous in-space animal track that also has an estimate of what an animal might be doing. And again, that estimate is mathematical. We have to interpret it, okay? The other thing I need to kind of talk about from the get-go is, and this actually came up in chatting with one of Nathan's students, Nathan back there, also named Nathan. And he was kind of asking me a couple questions, and it reminded me that I should really talk about the difference in the kind of data types. And so when we're using acoustic telemetry, we get these spatially discrete locations, right? So we go and we put our receivers out in the water, and so we're really biasing our sampling of locations, because we're only sampling where we put those receivers, whether an animal is there or not, right? But when we put something like a sat tag on a gray seal, what we can do is sample wherever that animal is going, and so we get this estimate of an animal path. And the models that we're seeing here today are useful only for animal paths, okay? And that's just because of the underlying what we call movement process that's describing those paths. And I'm not saying that it's not possible for detection data. I'm just saying that it's not there yet. So while we need to have data that are spatially continuous, luckily we have positioning systems, right? So we have positioning systems from the manufacturers, and of course we also have YAPs, which we flew Henrik all the way over here for the first time to North America to talk to us about. And so while we are continuous in space, though, most hidden Markov models out there, and the ones that we are looking at today, are discrete in time. Okay, so that means that your locations have to occur on a regular time interval. And that's just because of the way that we calculate the movement metrics. And it's, again, because of this underlying movement process, this underlying movement model that we're assuming. Okay, and I'll get a little bit more into that. So just remember, spatially continuous but temporally discrete for the hidden Markov models that we'll be looking at today. And so this is a mathematical/graphical representation of a hidden Markov model. And so we have two of these processes, which I've sort of already alluded to. So the first one is the behavioral process, and that's actually hidden from us, right? That's those two different colors. That's what we're trying to estimate. So we're trying to see, okay, I put my gray seal out there. Where is it traveling? Where is it traveling to a different grocery store, and when's it in that grocery store? Okay, those are the two different behavioral states. This behavioral process is assumed to be Markov in time, which means that the next behavioral state is only dependent on the previous behavioral state, and that's where the Markov comes from in HMM. You can also have Markov movement processes, and actually I think Henrik's code underlying it actually has a Markov movement process, but that is not indicative of the name. The hidden part, the hidden Markov part, comes from the behavioral process. And so basically what I have is I have this sequence of behavioral states that's evolving through time. So at one time step I'm traveling, at the next one I'm traveling, then maybe on the third one I'm actually in that grocery store, right? And so I've switched to a different state, and now I'm eating. And then what we also have is this movement or observed process that's, and I don't know, I've seen the arrows going both ways. So in some cases, I like to say have the arrows directed this way because I'm thinking in terms of a likelihood. I think most people, ecologists, would flip it around probably because they say, okay, that behavioral state is actually informing that movement process. So yeah, you should think of these arrows as pointing down. That was my problem, my fault. But basically you have this behavioral process that's informing the way you're going to move. And so for each of those time periods where I'm looking, whether I'm traveling or whether I'm in that grocery store, I'm going to be doing different things, whether I'm a gray seal or whether I'm in my car, right? So when I'm in that grocery store, I'm going to be moving a lot differently than when I'm in my car driving to that grocery store, okay? And so that's how those movement processes also evolve over time. So we have different sets of parameters to describe them based on the behavioral state that you are in. Does that make sense to everybody so far? Yes, Nathan.
Is the assumption then that the link between a behavior and an observed movement is constant through time? That the same behavior will always have the same movement observation? At least within like a range.
Can you repeat that one more time?
Is the assumption that the link, the arrow between a hidden process and observed process is consistent through the whole time? That essentially foraging looks the same one time as it does for the rest of the time that you observe?
Okay, so the question was whether the link between the movement and the observed process, the movement process and the behavioral process is constant through time. I think that's a little bit of a loaded question. For the example today, yes. It's kind of, the way that the link works basically is we have this movement process, and then we're basically fitting a model. So think about a linear model, right? And then we have this movement process, but then one of our covariates in that linear model, I guess, is a behavior. And so we're saying, okay, we're in this first behavioral state, then the beta values that you're assuming are going to change. But those beta values stay the same over the entire track, but it changes based on what state you're in. But so I'm only going, so when I fit a hidden Markov model to one track, I'm going to come up with two sets of parameters for that entire track. So it's almost like, here, I'm a whiteboard person. Okay. And then say this is our ARS behavior right here, and then we have more down here. The movement parameters for this and this are going to be the same, even though it's different time. The movement parameters for this and this are going to be the same for these models, okay? Sweet.
Primarily just dealing with two-state models, or are you studying for multiples?
You can have multi-state models, and we'll have an example of more than that. That's one of the main subjective choices that we have to look at, and there's a fair amount of research that discusses that because it's this trade-off between your kind of more statistical model selection techniques, which I think tend to favor more states versus our ability to actually interpret those states. And that's why I'm trying to really stress the fact that there's a difference between mathematically estimating these and then being able to actually explain them. Okay? Okay, so going back to the behavioral process, it's a Markov chain, which means, again, that the next state only depends on the state that previously occurred, okay? So whether I switch to being in the grocery store depends on only the state before me being in the grocery store. It doesn't depend on me 10 hours ago. It only depends on me 1 hour ago, basically. And so the way that we do this mathematically is through Bernoulli trials. So that's just flipping a coin, right? You flip a coin and you either get heads or you get tails. And this is, again, I think mostly in two states. This is extended, obviously, for 3 or more states as well. And that's kind of funny because I gave a 3-state example down here, even though using a Bernoulli distribution, but that's fine. And so these Bernoulli trials and I guess multinomial probability distributions are actually governed by the transition probability matrix. And so at any point in time, for example, if we have 3 states here, we're going to have the probability of staying. You can read this in terms of rows and columns. So the row down I like to read, this is being in state 1, 2, and 3 at time t minus 1. So my previous state. And then going across, it's 1, 2, and 3 at time t. Okay, so this probability here is staying in state 1 from time t minus 1 to time t. This probability here is switching from state 1 to state 2. State 1 to state 3. This is state 1 to, no, sorry. This is going from 2 to 1. So this is going from state 2 to state 1. This is going from 3 to 1. And then across here, it's 1 to 2 and 1 to 3. So all these diagonal probabilities are the probabilities of staying within each state. You'll probably more often see these as higher numbers, greater than 0.5, and that's generally one of the things that we look for, because if you're greater than at least, I guess in this case it would be, if it's 3 state, you would look more for 0.33, but when I have a 2 state model, if I'm greater than 0.5, it means that when I'm in that state, I'm going to stay in it for a while. So for a gray seal who's going out and traveling, it's going to travel for a while, but then when it hits a foraging patch, it's going to stay there for a while and it's going to eat a lot. So you're looking for higher values on these diagonals, typically. Okay? The other thing to note about this is that the rows are going to sum to 1, and that's because these are all probabilities. Okay? Sound good? Cool. So the movement process, these are typically done with random walks, and there are a couple of different ways that we can do this. But a random walk basically is just, it's an equation that's describing, and it's a probability, so it's a stochastic equation that's describing the movement of a particle as it's moving through space. And so these can be n-dimensional. You can have as many dimensions as you want. Typically, we have 2 dimensions. Some in animal movements, sometimes we have 3. A basic random walk here, so over there, the graph, that's an example of a 3-dimensional random walk. A basic example of a random walk here is just a 1-dimensional one where we have some position x along a line, and then we're describing that position evolving based on this error distribution. So I'm going to be at any point in time along this line, I'm going to be wherever I was previously plus some amount of random error is basically how it goes. That's what a random walk is. And so when we're talking about this in terms of movement processes and actually analyzing animal tracking data, these random walks can be done in a couple of different ways. So they can be done on the locations themselves. So that's what Henrich's process model does. They can be done on vectors of first differences. So that's what another model, the DCRWS, does. That's typically a state space model, though. On vectors of first differences, or they can be on the step lengths and the turning angles of a track. And that's what a lot of the packages use nowadays, and it's a very interpretable way of analyzing animal movement data, and so that's what we're going to focus on today. Okay, and so as I mentioned, these hidden Markov models are all done in discrete time, which means that, but the problem is that often we don't have observations in discrete time. And so the first thing that we really need to do is interpolate our track. And normally this is done with linearly interpolation. Which is, sorry, that's not like the most correct actually bullet, but you can basically think of linear interpolation as a weighted average between 2 locations based on the time difference between those 2 locations. So if I have a track here, if I have a track here and 2 locations here, but I need to interpolate it to here, then I'm going to calculate a weighted average between these 2 locations, and I'm going to get an estimate right around here. If based on the time differences, though. So it's based on the time step that you pick. And it's really important to note that this is an approximation to the real track. So it introduces a subjective choice, and that choice is the time step. And we will see that it can lead to some autocorrelation within your step length estimates. Does that make sense to everybody? Okay. Am I already 38 minutes in? No. Okay. Close though. Okay, so This is an example of interpolating a track again. So we have this continuous animal path. And then what I need to, all of these locations here though are regularly spaced apart. Okay, so they're averages of the two locations around it. The next step is to decompose your track into step lengths and turning angles. So what we do is we take those interpolated locations, which are in navy blue here, and then we calculate a step length, which is the distance between each of them, and then we calculate a turning angle, which is it's the amount that an animal is turning from its current heading. The third step is to fit distributions to these, and this is where the states come in. So we assume that these step lengths and turning angles follow different distributions, and we assume that those distributions themselves depend on the state that you're in. So you're going to have multiple sets of parameters, one for each behavioral state. Does that make sense to everybody? Good. This is a kind of silly example that I came up with like 4 years ago. I was anthropomorphizing male gray seal mating behavior, I think. And this is the fourth step basically is to calculate these behavioral states. And so the idea here is to show you that what we're trying to do is calculate, what we have to do post hoc is calculate the most likely path through all of the possible behavioral states that gave rise to the observed data that we have. So in my silly example, which maybe I did after watching a rom-com, I don't really know. The observations here are the mating success, so whether the male failed or whether it succeeded, and then the behavioral state is the behavior of the male, so whether it was mean or it tried to play cool or it was nice. And I'm not sure if you noticed, but the male only succeeded once it was being nice to the female, so it's not actually like that in real gray seal mating behavior, unfortunately. This is most often done, this kind of decoding is done with something called the Viterbi algorithm, and that's what we call a global decoding scheme. So what we end up doing is we're really focusing on the entire path. So we're calculating the most likely probable entire path through those behavioral states. And then finally, the fifth step is to check our residuals. And so there are ways to assess model fit. And the way that we typically do this is using something called the one step ahead, and sometimes they're called pseudo-residuals as well. And you don't really need to worry about that, but I put it up just as an example. But just like regular residuals, you can get stuff like QQ plots, and you can look at autocorrelation and other kinds of diagnostics. I think that's the last slide. That took longer than I expected, actually. So we'll get straight to the coding with John Pye's help, because he's incredible.
Very incredible.
Sweet. Did I open it up? I thought I did open up the R. Oh, yeah, we did. Is that good? Okay, let me take a break. Oh yeah, let's scroll up. Okay, so to do today, it's actually a leftover heading, but it works. We have 5 lessons to get through. We have until 5, right? Is that right? Okay. We have 5 lessons to get through. I am not sure if we will get through all of them, but we'll see. The first one we're going to do is just start by fitting an HMM, and we're going to use move HMM for that. And we're going to go over a couple of the different subjective choices, so looking at picking a time step, picking some starting values, and also interpretation of the states, and assessing model fit. Is this large enough for everybody, by the way, to see? I know everybody can follow along, but make it bigger. Okay, I might decrease it for some of the plots, just because it's... Nope, I don't know what I just did. There. Is that better? Okay, I might decrease it just for some of the plots, just to make it look because otherwise it gets really cluttered down there. But yeah, so the first step, we're just going to fit an HMM and look at the time step, starting values, and interpretation. In the second step, we're going to look at accounting for autocorrelation in the step length residuals. In the third lesson, we're going to look at picking between different numbers of states, so that's another assumption that we already alluded to. And in the fourth lesson, we can look at fitting to multiple animals. And finally, in the fifth, we're going to try to fit to some data which is seemingly a little bit messier. And so, yeah, just to give you an overview about the data, I guess. So we're going to look at two different kinds of data. The first one is YAPS output. And so we have two different pike that Henrik kindly gave to me in terms of the YAPS output. And so we're going to fit it to that first. And in the second one, we're going to fit it to some Telma pinpoint data. So I know there's a lot of interest in fitting hidden Markov models to these positioning system data, or these positioning system outputs. I'm going to fit it to the crayfish data that we just got introduced to. I'm going to attempt to fit it to the crayfish data that we just introduced to. And we're going to see that there are a few more issues when it looks like the data might be a bit messier, might have some more measurement error that haven't been accounted for. So that's a really big difference between something like Henrik's model, which accounts for measurement error in a stochastic manner, versus something like, as far as I know, these positioning systems which use deterministic equations to estimate this animal track. But you get a few more errors in it, and so it can be really hard to figure out what those states are because there's noise corrupting the track. And that being said, I think those crayfish data are just harder in general to estimate anyway. So I don't think we have the same kinds of problems with other positioning system data sets. I think that's a little bit of a trickier example. So I always start by removing all my objects and setting my working directory. To do this, you would have to change. I think it comes off when you download the folder as -master, so you would just have to change that. Does everybody have working directory stuff set up? Because that's very commonly an issue. And I know we've been through several different lectures so far, but it came up last lecture too, so. Okay, good. So after that, you can load all of or hopefully you guys have installed all of the packages. Is that correct? Yeah, that's right. Okay, so I updated that on the README. I forgot to update that on my actual code. But the install package line for move HMM, you just need to do install.packages, like a regular package from CRAN. I was trying to install it from GitHub because I thought there was a vignette available, but I guess there wasn't, and I just thought there was. And I thought I saw it on my computer, but I guess I didn't. You can find it online, though. So yeah, let's just go ahead and load all of these packages. It's good. It's always good to note, too. Here, let me just increase this. It's always good to note these kinds of kind of warnings when you're loading packages. So whenever we have something like this, it suggests that different objects are masked. So if you want to use something, if you want to use dplyr groups, for example, here, you're going to have to put dplyr : groups, because what this is saying is that MarkMod Mover actually has a function called groups that's masking this, or it has something called groups that is overwriting whatever is in dplyr. Of the code again? Okay. Ugh, stats. Okay. Yeah. Nope. That's not what I want. Okay. Finish loading all of these packages. I like to do it slowly just to keep note. Perfect. Okay. So this first lesson, again, we're going to just fit an HMM. We're going to look at picking a time step, picking some starting values, interpreting the model, and assessing model fit. So to bring in the data for this entire tutorial, actually, we're going to just load this RDA file, and we can take a look at what's in that file, what we just brought into our working space. And so We have a couple different things. Here we have cray 34, that's the crayfish example, which we'll get to at the end of this, hopefully. We have hydros, which are the receivers that were used to track the pike. We have a lake outline, which is the lake that the pike were in. And we have two outputs from YAPS. We have YAPS 1315 and YAPS 1335. So those numbers just show you the ID of the pike. World is a shapefile that I've incorporated here. That's just from Natural Earth. And that's just to plot some of the data later on. So here's an initial view of the data. And thank you, Henrik, for giving me a little intro to the YAPS stuff. So here's the lake. That's all of the receivers, and these are the different tracks that we're looking at. So we have two pretty different tracks. One thing you'll notice here is that we do have a ton of receiver coverage, and so it'll just take a little second to update here to show you. But we have a ton of receiver coverage throughout this lake. There we go. Ton of receiver coverage throughout this lake, and so that's just in contrast to the crayfish data which we saw before, and that's just a big factor that can lead to more accurate results, I think, in both your positioning system algorithms and also your YAPS. Okay, and let's take a look at the YAPS data. I always use head. I don't use the view thing, because typically when I have RStudio up, I just have this portion, and they're side by side, and they're filling the screen. And then occasionally plot comes up, and I get rid of it. So let's take a look at all of the variables. So here, just like Henrik was telling us, he does everything in UTM. So we have X and Y, so that's northing and eastings. We also have standard deviation of X and Y. It's really important to remember that we are fitting these hidden Markov models to predicted variables from a previous model, okay? So just like you're taking a model, or I can't even think of an example that would relate, but your data aren't observed data anymore when we're fitting it to YAPS, okay? And that's okay, that's been done before. I don't think it's been fully studied what happens when we do that. But so it's just something to keep in mind for now, okay? The other alternative is fitting a switching state space model, which is pretty hard. But it's doable, obviously. And so just keep in note that the projection is UTM 32 north, so that's the unique EPSG code that we can use, and we'll use that a little bit later, I think. SDX and SDY, again, are those standard deviations. TOP, that's the time of the pings. That's the timestamp that we're looking at. NOBS, we don't use that in the hidden Markov model, but that's the number of receivers it was detected on, right? Right, Henrik? NOBS is the number of receivers it was detected on? Yes. Yeah. And then velocity, is that velocity of the tag or is that velocity of the sound?
It's the sound velocity.
Okay, that makes more sense. I was going to say, I didn't know how we did that. Okay, and velocity is, the speed of sound at the time, which Henrik also estimates, which is really cool. And so we don't need these NOBs and velocity, but I just leave them in there. So let's first start by just plotting the data. And I'm going to do this with confidence interval because, again, this is model output. So to do this, you just take your positions, subtract 1.96 times your standard deviation, and plot it on both sides. Let's do that again so it's easier to see. That's your track. That's your lower confidence interval. And that's your upper confidence interval. So it's doing okay. You know, it's good to look at this because, again, that standard deviation is going to tell you information about how accurate the model thinks that your positions are, okay? And just stressing that we're fitting this to predictions, not observations. Here's the other track. Lower confidence interval. Did it already put? Yeah, I think I already did the upper one. You can see a couple places where this is maybe getting a little, where there's a little bit more error. So maybe right here, there's a little bit more error than normal. Right here, there's a little bit more error. Right in here too, as opposed to right along here. It's pretty much straight. It's probably in relation, I would say, Henrik, you can pipe in, but it's probably in relation to just the number of receivers that you've detected your animal on. If you have more information when you're fitting state space models like YAPS, then it's going to predict it better. Just stuff to keep in note. Nothing there is really concerning, but it's always good to look at. I also always like to take a look at your locations through time. So I look at lawn through time and lat through time. And the reason I do that is, like we saw before with Henrik and with the crayfish data, you could see that there were some significant gaps there. And if you don't know about those can they can certainly complicate your model fitting when you're doing an HMM. So here we're just looking at longitude through time. Here we have latitude through time. I don't know if that's switched yet. It didn't. There it is. And this is kind of interesting. This one isn't super informative, but we do see that there's no gaps. Nothing really looks out of the ordinary, although there is kind of a cyclical change, so it kind of looks like the animal is going back and forth through these axes a little bit, but the variance is spreading over time. So it's almost like it's moving more over time. But that's hard. That's a little hard to interpret. If we look at the other one, though, this is showing some interesting behavior, I think, because it looks like there's some residency behavior here where it's not moving at all, right? So in both of these, especially in this one, you can see these spots here where the animal's clearly moving through time, maybe shifting. It's weird, it's like reversing along the axis there, but you can't really interpret that unless you're looking at both axes, right? But then there are parts here where it just kind of staircases, right? And so that looks like the animal's not really moving, right? So it's actually looking like it's not shifting whatsoever. And again, it's hard to interpret that because you can't just look at one axis and say this animal isn't moving. It could just be moving along a line of longitude or latitude, but they occur in both, right? And it kind of looks like those line up a little bit. So it's just interesting to note because that can be indicative of different behaviors. Yeah, John.
Could these pretty much positions be different between the two fish because they were attacked at different time different flags? I think the one that you're showing at 1315 was 30, and 1335 was 60 to 120.
Oh yeah, that's right.
Or is it the other way around? I don't remember.
What were the different time differences, though? What were the different time differences? Again? 10 to 30 seconds, and then 60 to 90 seconds. So that definitely does, that could definitely influence it, especially if we're comparing between the two. I would say that if this was, even if this was the shorter one, I mean, we're looking at almost a day, even in this spot, right? So if we're looking at almost a day right around here, and we're definitely looking at about a day here, and almost another there, that's residency, despite being pinging only on a, 90-second interval. So it's just one thing that you can look at. Again, I like to look at it more with gaps. It's more relevant for the, I like to do this more to look at gaps, but that's more relevant for the crayfish data later. And this is kind of, if you start to think about the biology of the animal, and somebody can definitely correct me here if I'm wrong, because I know nothing basically about pike. But pike are burst swimmers. So we would expect to see probably at least two behaviors, right? So you're going to have a sit and wait behavior, and then you're at least going to have a burst and hunting behavior, right? But that burst and hunt behavior might be a little hard to actually get with a hidden Markov model. And that's because I assume that's going to be really quick, right? That's why it's called a burst. So it's going to be pretty quick, which means it's not going to show up for a longer period of time, which means it's going to be harder to estimate, right? So this we definitely see some residency behavior here, I think. And so that makes sense that maybe that animal is sitting and it's waiting for prey to come around. I'm not sure if we can actually get burst behavior out of a hidden Markov model. So that directed, and also that directed, the amount that it's moving in between those kind of stationary times is definitely more indicative of maybe I'm going to go look for a different area to sit and wait, as opposed to I'm bursting for that amount of time. Okay, so I think that was important for me to start and think, because we clearly have two behaviors here, but that burst behavior probably isn't showing up. So we might be looking for more than two behaviors in our hidden Markov model. Okay, so the first thing that we need to do is interpolate the data onto a regular time interval. So in order to do this, we do need to pick a time step, and there are a couple of different schools of thought on this. So one of them is to pick a time step based on the distribution of your actual differences in detections, basically. So the distribution of time differences in between your successive locations, right? And then the other one is you want to also think, again, about the biology of the animal. But that one's a little bit harder. But if you're thinking about how long you would expect your animal to be in residency period, in a residency time for it, and like how far it might travel in that, that's more based on the model parameters and stuff. And so if you think about a gray seal, it might take 3 hours to traverse a foraging patch in one step. And so when we're doing ARS behavior, we're bouncing back and forth, right? So for a gray seal, it might make more sense. And this actually came from Benny Novak. I feel like I should mention her, because she was the one that first told me about that, and that made a lot of sense to me, because it really, because we actually sample those animals every 5 to 15 minutes or so with the tags, but it doesn't make sense necessarily to have a 5 to 15 minute time step, because the ARS behavior we're looking for would occur more on a 3 hour long time step or 2 hour long time step. So, but regardless, a good first place to start is by trying to pick a time step that will give you the same number of observations coming out as you're putting in. Okay, so if I have 1,500 observations, I want to temporally interpolate so that I have another 15 observations, as opposed to really decreasing that sample size. Can I get some water? How are we doing for time? Ooh, 1 hour. We can do it. How's everybody doing so far? It's okay? Good. Oh. Okay. So when working with time, I'm going to do this for now because we don't need that. So when working with time, it's just good to note that the regular diff function will pick the units for you. So do you guys know what the diff function does? Okay, goes along a vector, takes the successive differences between each spot along a vector. So if you want to specify the units, then you need to use diff time, and you need to supply 2 vectors. What am I doing here? First, what I'm looking at here is just the time of the pings. This numeric density plot is just the timing of the pings. So I'm actually kind of confused. Oh no. So here what I'm looking at is the difference in the timing of the pings. And so we see here this is coming out in minutes, I think. Minutes aren't really good to use. I want to use minutes. I normally use either seconds or hours. Obviously, because we're looking at pike, I'm going to use seconds instead of hours. So this is me using diff time in order to be able to control those seconds. So what I'm doing here is I'm just taking the time of pings vector. I'm taking out the first one, and then I'm taking the time of pings vector, and I'm taking out the last observation, and then that's going to give me all of the time differences, just without using the diff function. So here we see the same density distribution of those time differences. And we can see that it's centered right around 90 seconds. So we're looking at that 90-second animal. And that makes sense that we're going to have a little bit of variation around it because it was random within the 60 to 120 second interval for the time of pings. What am I doing here? Yeah. Here, I'm just calculating the mean just to look and see what that mean is, but I was pretty sure it was 90 seconds. And as a result, I feel like a value of 90 seconds would probably be a good way to start in terms of interpolating our data. So now to interpolate the data, I brought in a different function. And the reason I brought in this function is because I haven't seen this part as part of the move HMM package. So I just did this myself. I could be wrong, but. So here this function depends on an animal object, and it depends on a time step. Here I've encoded that time step to be in seconds. Animal has to have the date, time, and POSIX. And then you're going to have your longitude and latitude, or your UTM coordinates, so your eastings and your northings. Eastings and the northings. And the column names have to be date, X, and Y. So to start with just to go through this function really quick, I guess. You take the first observation, you take the last temporal observation, and then you calculate a regular sequence between those. So that's just me calculating where I want those locations to occur in terms of my time scale. And then you use something called the approx function, and that's going to linearly interpolate your track. Okay? So we can just run this function, and then interpolate the first Pike's data. So YAPS 1315. I just renamed here the date column or I renamed TOP to date to work with my function. Then I run my function using a time step of 90 seconds, and then I just write assign this Pike. I have an interesting medley of piping and dplyr and just regular base R. I just learned about piping last summer. Again, Rob actually taught me about that. So yeah, I just do whichever one comes to mind first. And sometimes I write assign because when you are piping, as Rob likes to say, you are doing and then. And so you're reading your code from left to right. And so I'm going to write assign because the next thing I do is assign it Pike. And that's why I do that sometimes. Take a look at it. We get out the date, we get the X, and we get the Y. So now our locations are named X and Y. So this is, again, easting, northings, or longitude. This is eastings or longitude. This is latitude and or northings. But in our cases here, we're working in UTM. And then what you want to do is check that all the points actually lie on the path, because if they don't, then something went wrong, and that needs to be fixed first. So here you just take the YAPS data, ggplot it, add a path, and then add the points from the interpolated data. I really like cadet blue, so I like to pick the colors. I think this is the example that I actually used in the PowerPoint presentation. So here we see all of our points, which are the interpolated part, actually lie on that path. So that's good. So now that we have locations occurring in regular time, that next step is to decompose the track into our step lengths and our turning angles. And so there are a few ways to do this, and different packages do it in different ways. But basically, the way you do it depends on what kind of coordinate system you're in. So if you are unprojected, if you're in Latin lawns, then it's better to use spherical geometry. And if you are in UTM, then you want to use Euclidean. So Euclidean is basically whenever you're projecting your Latin long coordinates, basically what you're doing is you're saying, okay, this is the most representative two-dimensional plane where we can calculate distance, etc., along that graph. So you're taking a curved part of the world and putting it on a plane, right? And so you need to use different geometry to calculate the step lengths and turning angles than if you don't project your data. You leave it in Latin lons, so then you have data on a sphere, and then you need to use different geometry to actually calculate those. This stuff is all done for you, though, in the packages, so you don't really have to worry about it. So with move HMM, you can do either, actually. And the way you do that is using the prep data function. And again, Teo actually has a really good vignette out there. If you just Google it, it comes right up. And he does all of this stuff and more. So here, this prep data function, it takes your data, and then you need to specify what kind of projection or lack thereof, basically. What kind of coordinates you have. So you either say UTM or you have Latin lon. So here we have UTM, that's what we specify, which means we're going to be using, oh goodness. Okay, how did I miss that? Okay, so here we have UTM, that's what we specify. We can take a look at this data structure now. All the prep data does, it calculates the, well, it does a couple of things, but it's not going to alter your data. It's just going to add to it. So it adds 3 new columns. The first one is an ID, and we'll come back to this later, but you can actually fit this model to multiple animals. So if you don't put an animal ID in, though, it's going to put one in there for you. So I could have put 1315, but I didn't. Then it's going to calculate the step length, and it's going to calculate the angle. So this is a step length in between successive locations, and again, this is on the interpolated data now, so we need to remember that. And then these are the angles in between those different locations. Yeah, good to note that these angles are actually in radians. So normally we think about angles in terms of degrees, right, between 0 and 360. So if you need to convert in between those, then you just multiply by, well, if you want to go from radians to degrees, you're going to multiply by 180 over pi. The other thing you can look at here, just to be aware of, it's just good to know, is that these NAs. So these NAs are caused by the fact that you need multiple locations to calculate a step length and to calculate a turning angle, right? So to calculate a step length, you need 2 locations. Does that make sense? Distance between 2 points. To calculate a turning angle, you need 3 locations. And that's because you're calculating the angle between 2 vectors. And so I need 3 locations, all right? And so here, the position of these NAs suggests that, let me see if I get this right. I'll just read it off. Okay, so this suggests that the step length from time t minus 1 to t and the step length between t minus 1, t, and t plus 1 are going to be informing the same state at time t. So that's just good to know. So it's basically saying that this step length and this turning angle are informing this behavioral state, okay? So now we can take a look at the distributions. This can be a little bit tricky to figure out, but nicely, move HMM actually has a generic plotting function for the process data, so you can just plot this. It's going to prompt you. There's our data set for animal 1. These here are the step lengths and the turning angles in between minus pi and pi over time. So you can see here that we do vary quite a bit. We have a lot of large step lengths. And then we have some, again, it looks like residency periods where these step lengths have really decreased. And then these are also transferred into frequency distributions. So just looking at frequency plots here of the step lengths and the turning angles. Now what you need to do is take a look at the density of these different distributions, of these different observations now. So now we're treating the step lengths and the turning angles of the interpolated locations of the YAPS output as our data, okay? So again, we're doing stuff to our data that we need to keep in mind. These are all assumptions that need to be reported in papers, right? So here we have your step length density, your step length histogram, turning angle density, and turning angle histogram. I just like to look at both. So our objective here is to look for multiple states. And in modeling terms, again, this means that we're assuming that observations shouldn't actually be modeled with just one underlying probability distributions, with one underlying probability distribution for each of these. So, for example, for each of these, we're assuming that there are multiple distributions that are acting together to give rise to this empirical distribution here. And by empirical distribution, I just mean the one that's actually calculated from the data itself. But then we're going to model it, and that's going to give us a different distribution. But so we're assuming that there are multiple states underneath, and there are multiple distributions that are giving us those observed ones. So in an HMM, we want to estimate those multiple densities and the states that relate to them and the entire path through the curve, through the entire path sequence of states through the path. And I can't remember why I did this. Oh yeah, so the way we do this is by doing something called both move HMM and Markman mover use maximum likelihood estimation, which means that we are optimizing a function, basically. And in order to optimize a function, we need to be able to provide it with starting values, okay? So starting values, again, are one of these choices that are a little bit more subjective within a model, and they can definitely rise to, or give rise to different parameter sets and parameter values and model fits. And so it can be pretty important to test these models with multiple different starting values. Sometimes it gives rise to different model fits, other times it doesn't. So yeah, so this first one of these steps that we need to do is pick different starting values. And so you need to think about the distributions that describe your turning angles and your step lengths, okay? And these two packages give you multiple different distributions. We're just going to focus on, we're not really going to focus on different choices between those, but there are different choices, basically. And so we're going to use a gamma distribution for the step lengths. And then for move HMM, we're going to use a von Mises distribution, which is basically an approximate normal, but it's on a circular distribution. So it only goes from minus pi to pi. For Markman mover, we'll still use a gamma, but we're going to use a Rapt-Cauchy instead. So it's important to kind of get a sense of what these different distributions look like. So you can look at the gamma distribution here just to get a sense of it. Gamma can be tricky because it's got a shape and it's got several different parameterizations. So in order to be able to sample here from R, you need to parameterize it either in terms of you need the shape, and then you either need the rate or the scale. Scale is just 1 over the rate, basically. So your scale parameter here is going to be an estimate of your spread of your distribution. So your rate is the opposite. So the higher that your rate is, the less variation you'll have. So we can just take a look at, like, the best way to do this, honestly, is just take a look at what happens when you plot different values for these gamma distributions. And so in this first one, I'm parameterizing this in terms of the rate parameter. So I'm keeping that at 10, but I'm increasing the shape parameter. And so you really notice that the shape parameter changes the shape of the distribution. Okay? So it's not just changing the shape in terms of the mean, it's also changing things like the amount of tailedness in the distribution and how peaked it is. Also known as skewness and kurtosis. In this next one, I keep the shape parameter constant, and then I increase the rate. So you can see that they kind of interact a little bit. Then we can take a look at the von Mises distribution. this distribution has a mean, and it's got a concentration parameter. So that mean is just a mean. It's where you're expecting the most likely value of your distribution basically to occur. And then the concentration tells you how, it's kind of like the opposite of a variance. It's telling you how concentrated your probability distribution is around that mean. It's kind of the opposite. But. So we can plot these two. So here, well, let's start that over, sorry. So here I have a mean of 0, and then I varied the concentration. So this first one has a pretty low, it's a lower concentration, so we're not as peaked around that 0 value, right, around that mean. This second one here has a higher concentration, so we're way more peaked. So it means that in our example, it would mean that more of our turning angles are going to be around 0. Is everybody following okay? Okay. Am I going too slow? Okay. In this next one, I've changed the mean distribution, or I've changed the mean, and so now it's centered at pi. And so because we're centering the graph at 0, it's going to look weird, right? It's going to look like it cuts off, but it doesn't because it's a wrapped distribution. So it just keeps going around and around, basically. So I've centered it at pi, and again, we have that lower concentration, and then we have that higher concentration. So now we need to pick a set of starting values, and Teo and Roland did a really good guide on how to pick starting values and how they like to pick starting values for their data sets. The way I typically do it, I just overlay a few different sets of these curves on my histograms. Just kind of roll with it and see what happens. Typically, we're going to start off just looking at two states. And how much time do I have? We're going to start off just looking at two states. And typically, when we're doing that, especially in the gray seal idea, we have these stretches where we're taking long, if we're looking at ARS, we have these stretches of time where we're taking longer steps that are more directed, right? Because I'm hungry, so I'm going to my grocery store. So I'm going to go quicker. I'm going to keep going the same direction because I know where the best fish are, right? And then when we get into this spot here, when I get to the grocery store, I stick around in it. I'm more exploratory, so I'm taking smaller steps. I've slowed down because I want to stay in there. And I'm also varying my turning angle a lot more, right? Because I'm going all up in that grocery store. It's been a long couple days. Fun though, it's been great fun. Okay, and so what that ends up translating to when we're talking about these distributions is we want longer step lengths associated with, a more directed angle. And then we want shorter step lengths associated with a more spread out angle. So here, I actually overlay 3 potential distributions over here. So this is our gamma distribution for our step lengths. These step lengths here are going to be associated, because this is the longer ones, these are the ones that I'm looking at to be associated with my traveling behavior, basically. These ones here, in the lower ranges, those are the ones I'm looking to potentially be associated with whatever kind of residency behavior I'm looking at. And here I kind of fitted a third state because I think that there's I just looked at it, because I think that there's quite a few outliers here that are a little bit harder to capture. For the turning angles, what we're typically looking for again is when we're looking at directed movement, we're going to look at a really concentrated distribution around this 0 angle, right? Because if I'm going 0 degrees, turning 0 degrees, I'm going to be going straight ahead. And then what we're looking for, more often than not, what we end up looking for is more of just a flat distribution that's centered around 0. But in these data, in this Pike example, it looked to me quite a bit like there was actually another peak centered at pi. More often than not, just looking for a flat distribution. In my experience, More often than not, we're looking for a flat distribution that's associated at 0. And that makes sense too, because when you're going to an area and you're searching in the grocery store, or you're in that residency period, then you could just be randomly moving around, right? In this case, it looks to me like that animal is actually course reversing. So it's going back and forth, kind of going forward and backward a bunch, possibly. So that's why I was looking at a distribution centered around pi instead, just because of that extra little bump. So now, based on these distributions, I'm going to go with those for starting values. And I think for the first two, for the gamma ones, I just picked the first two here, the first two that we saw. So I didn't take that really long tail one, that long flat one. Just pick the first two. A little bit of the problem with this is that the problem with the way I do it is that move HMM actually parameterizes, in terms of the user interface, parameterizes the gamma distribution in terms of the mean and the standard deviation. So you actually have to take those parameters and calculate the mean and standard deviation of the gamma distribution, but you can just find those equations on Wikipedia, and I just included them here. Hope that's right. We're rolling with it. So here I'm calculating my init, so initial distribution or initial parameter estimates for the mean of the gamma, for the step length, and then these are the standard deviations. Mean and concentration for the turning angles. Now we can fit a model. So we run this. Might take a little second. We can just talk really quickly about these arguments. So the first argument, obviously, is your data. And you have to input the prep data object from MoveHMM. The second argument is the number of states. So here I'm telling it, I just want to estimate 2 states. I'm just going to look for 2. Then you input your initial values for your step distribution, initial values for your angle distribution. And then you can input a formula here, and I didn't even plan to put this, and I definitely wouldn't have had time anyways. This formula here is actually a way of relating your step length, or sorry, not your step length. It's a way of relating your switching probabilities, so that transition probability matrix that determines what state you're in and whether you're switching between states. It's a way of relating that to a covariate that might be associated with your data. So if you have lat and lon, for example, and you've also estimated depth along your track, you can relate it to that, right? And that makes sense because I can say, okay, well, maybe I only forage when I'm deeper. So that's going to give me way more information about whether that animal is foraging or not, and whether it's going to switch into a foraging state. Yeah?
Can that covariate be something that the animal is measuring, like if you have a sensor tag or something?
Totally. I think it's better if it's, so I actually don't work a lot with covariates. But I imagine it would be very hard to use something that's extrinsic to the tag, because then you have a spatial and temporal scale that you need to interpolate over. Like, say for example, if I have sea surface temperature, and then you get that every day or so, that's a much coarser time scale than your animal movement path. And you're going to have to interpolate it somehow along the path as well and figure out what observation to use. Yeah?
It's not habitat. So those, like a seagrass system,
Yeah.
like it's fragmented or not.
Is that a question or a statement?
No, that's a statement.
Yeah.
That's something that's like extrinsic from the tag.
Right.
Could be added.
That's a good point. Yeah, that's a good point. Yeah, I guess I was thinking more environment. Yeah, that's a really good point.
What if the sensor was measuring something about the animal and not the environment, and use that as a covariate? For example, like if you had an EMG tag and you were measuring muscle activity in the animal, would you use that as a covariate?
What's an EMG tag?
Electromyogram tag that measures action potential of the muscle of the fish.
Yeah, sorry. The question was whether we could use something that is, sorry, what was the question again?
So instead of using an environmental covariate,
Yeah.
you could use another covariate about the animal, like either.
Yeah, definitely. So the question was whether you can use another covariate about the animal. So the first example I gave was depth of the animal. So yeah, so you could definitely do an EMG tag as well.
Wouldn't that be an environmental covariate though?
Sorry, I was thinking depth of the animal at the time. So like from a pressure sensor as a,
That's what I'm asking is, can
I don't see why you couldn't. Yeah. But again, I don't work a lot with covariates. And then you have to specify what step length and angle distribution you're using. I think these are both defaults, so you don't really have to specify those ones. Oh yeah, sorry.
So how do you bring like all these covariates that we're talking about together with whatever the formula is?
It's like a regular LM formula,
Okay.
as far as I know. Yeah. Yeah.
But like in keeping with that, do you have to worry about if those covariates correlate with one another, like step length and heart rate? Because obviously heart rate is going to go up as the fish swims faster, and so does heart rate. Does that cause problems in the analysis?
So the question was whether you have to worry about correlation in your covariates when you include them. So I think in that case, it wouldn't matter as much. So again, I haven't really worked with step length, or sorry, with covariates, and now I'm regretting bringing it up. But or I'm regretting not doing it for this, because clearly it's important. That one, I don't see it being as much of a problem because you're modeling the step length, like the step length distribution isn't a part of that formula, right? The step length distribution is outside of that, so it makes sense that they would be correlated, right? If you think about if you were just modeling in a linear model step length as a function of heart rate, that makes sense, right? As opposed to doing something else as a function of step length plus heart rate, I think. Yes.
Another question about the
Sweet.
how would you decide, for example, with the heart rate, to put it in the covariates and not in the HMM model itself? Like in addition to step and angle, like
So the difference is that these models have been specifically tailored for step length and angle. So I'm not sure if it can incorporate. It might, but that depends on the package, whether it can actually incorporate a third observation. And I know Roland at least has worked with lots of different observations. He has a couple of great papers out there, lots of different kind of, more than greater than 2 observations. I don't think it's a part of this package, so you wouldn't be able to incorporate it. Yeah, I could be wrong though. So, are we clear on the covariates? Okay, cool. So now we can take a look at the model output. So here, this first part here, this is the value of the maximum log likelihood. You probably won't really look at this very much, but this is used in their calculation of AIC. This is just the value of the function at the maximum of the parameters. Although I wonder if it's the negative log likelihood, but it doesn't matter. These are the step length parameters. So here we have a mean step length of 11.48. And then for our second state here, so we have state 1, state 2, and then the parameters mean and SD. So the mean step length for state 1 is 11.48, and these are going to be in whatever units your projection was in, because we put in UTM. So it's going to be meters. Right, Henrik? We had it in meters. Yeah. And then this mean over here is going to be 1.56. So we can see quite a bit of overlap here already, which is cool. Standard deviation. This makes sense. So this is your standard deviation of your gamma distribution. These are just also different between the two states. And then we can look at the turning angle parameters. So here it says state 1 is centered at 0, and it's pretty concentrated. We have a concentration parameter of 3. State 2, it's not quite centered at pi, or minus, it's not quite centered at pi, which is 3.14. But it's centered a little bit off of 0, so it's centered right around here. But for all intents and purposes, it's basically around 0. And we can see here that it has a really low concentration value. So this distribution is almost flat. So instead of what I thought was going to happen, which was we get a second parameter distribution that looks like this for the turning angles, we're getting something like this. So the mean doesn't even really matter that much. It's flat. What else do we have? Regression coefficients for the transition probabilities. We're going to skip that. Those come into play, though. These will just come into play. We only have an intercept because we don't have covariance, okay? They come into play if you have covariance. And then you'd be able to interpret those regression coefficients in the same way you would as a linear model. This is your transition probability matrix. So this is telling you that if you're in state 1, you have a 92% or 0.92 probability of staying in state 1 from each time to the next time. If you're in state 2, you have a 0.96 probability, 0.97 probability of staying in state 2. And then this is the probability of switching from 1 to 2, and this is the one of switching from 2 to 1. Okay. This is the initial distribution. In this case, it's the starting distribution of being in each state. Pretty sure. You can set it to the stationary distribution, which is kind of like a long-term behavioral, long-term statistical behavior. So long-term, the probability of being in either state, state 1 versus state 2, would be equal to this. But here I didn't set it to the stationary distribution. A really good function to plot everything. So here we have a plot. So we have our frequency histogram of the step lengths, and then we have the two different distributions that were fitted. So this is state 1 in orange and state 2 in blue. So state 1 here is going to have those longer step lengths. And state 2 has the shorter step lengths. Go to the next plot. So now we're looking at the distribution of the turning angles. So state 1 here, which had the longer step lengths, is also much more concentrated around 0 than state 2, which again is extremely flat. These dotted lines are just the sum of those two distributions. Oh, sorry. What's up, Rob?
If you go, I guess, kind of back and forth between these two plots, from your experience using these models and seeing the many different shapes these can presumably take for different individuals, how do you interpret it when you look at these? And what kind of distributions do you see? And what does it kind of tell you about what the two states could be or how they're behaving? Is there any, I guess, to summarize, does experience give you the ability to ascertain anything specific about the data from looking at these two plots?
Well, I mean, these distributions are how you interpret. So the question, I don't know, there was like 4 questions. So,
I've been transposing them into the chat.
oh, okay. So the question was,
Can you learn anything specific about the data from just from looking at these plots?
can you learn anything specific about the data just from looking at these plots? Yeah, so, I mean, these plots are the ones that suggest whether there are multiple states or not, right? Along with the parameter estimates. So if you had parameter estimates, if we went back up here, and if these were the same, then you're not likely going to have 2 states. Another way that you can see, yeah, I'll get you in a second. Another way that you can see if you might only have 1 state is if your probability of switching to the other state is 0. So if I had, in this transition probability matrix, if I had a probability of 1 here, and I started in state 1, then I'm going to stay in state 1 forever. And so that would suggest that you don't have 2 states. Does that make sense to most people? Okay, Nathan?
What would suggest that you have 3 states?
What would
More than what you guessed.
Yeah, what would suggest if you have 3 states? So a lot of that is probably just how you want to interpret your data and what you want to look for. I look a lot at model fit too. So whether you can capture all of the behavior kind of. So I guess in terms of this, if you maybe had more outliers out here that clearly were not a part of the distribution, that would suggest something. But I might have some more notes in here about that. Hopefully we get to it. Oh my gosh, okay. I'm gonna blast through this a little bit. You can look at the confidence intervals. Oh no. Okay, yeah. So they also give you a plot here that just plots your data and gives you the two different states. So you can see here the blue does look to be more associated with some kind of residency. Yellow is clearly some kind of transitory behavior. And that makes sense. So you can look at the confidence intervals. These are important to look at. Just confidence intervals of your parameters. So we're pretty centered. They're pretty small, which is nice. It's good. We can take the states out. And by take the states out, I mean calculate them and save them. And then we can take a look at this. So this is what the state vector looks like. So they encode in 1s and 2s. So when you have these high probabilities of staying in each state, you're going to have longer runs of 1s and 2s. But those are obviously also going to be influenced by your movement metrics, so your step lengths and turning angles. So then I like to look violin plots, also something Rob taught me. And these show you, right here what I've done, oh yeah, I should explain this. So right here what I've looked at is I've taken the RLE of the states. So if we look at this, what RLE does is it calculates the lengths of runs of each value. So I'm saying, okay, I had 17 ones to start off with. Then I switched to 2 and I had 18 of those. Then I switched back to 1 and I had 17, 18. Then I switched back to 1 and I had 7, switched back to 2 and I had 4, okay? So I'm calculating basically the time that each state lasted for. And so you can see that typically here in this plot, you have a lot more, oh my gosh, this is gonna die. So here what you can see is state 2 has these longer runs associated with it. And I think if we did that right, state 2 was the more resident behavior, right? State 1 was the one where the animal was traveling longer. So what we're saying here is that there are some pretty significantly long runs or long periods of time where we're staying in that resident behavior as opposed to being in that, compared to being in that traveling state. Okay, you can also, again, plot the residuals. This is super important. So here, we have a couple different plots. First, we're looking at, so in the first column we have step lengths, in the second column we have the angles. So here we're looking at the pseudo-residuals. Again, they call it pseudo-residuals. I think it's the same thing as the one step ahead residuals, pretty sure. So we're looking at the pseudo-residuals over time, and by time I also mean observation. So you want to look for no patterns there. Obviously we have a lot of observations, it's a little hard. You can also look at the angle one. Then you can look at the QQ plot here. So we assume that these pseudo-residuals follow a normal distribution, so we can use a QQ plot to look at these. So here we have a little bit of variation around it, but I've seen way worse, so it's not bad. Here's the part that's a little bit more concerning. We clearly have quite a bit of autocorrelation in our step length distribution, in our step length residuals. So there's something going on there where the step lengths are related to themselves that we should probably account for. A couple different ways that you could do that. So one, you could try to use a coarser time scale. That might shift your interpretation of your states, but we haven't really even talked about the interpretation of these states yet. I was going to do that a little bit later. So one, we could look at a coarser time scale, and that makes sense because if you have a finer time scale and you're interpolating over that, then you're going to have multiple observations that are just closer to each other, so they're going to be more related. You can also look at different starting values in case we're not on the optimum. And sometimes that happens just because you have a bumpy likelihood. So you have a probability distribution underlying this that's kind of bumpy, so you can get stuck in a local optimum. Yeah?
Is there any way to look at the likelihood
I don't know if you can do it from move HMM. Like, I don't know. I could hack a way to do it in MarkMod Mover probably. Or ask Ethan very nicely. Yeah. But one way to just tell is just by using other starting values, right? So you could also try accounting for autocorrelation using MarkMod Mover, which is the second package we'll use. And I think we're only going to get through the first 2 lessons of this today. Just fine. So I'm sure it's fine for you guys, right? You don't want to stay here an extra couple hours, do you? So the first thing we can do is try that coarser timescale. So here I'm just multiplying my time step, which was 90 seconds, by 3. And I'm calling it Pike 4.5, 4.5 minutes. Nope, that's not what I wanted to do. There we go. Plot the 2 data sets. So here I'm just plotting the different interpolated data sets. How's everybody doing so far? We're okay? Okay. Soon we'll go to good robot. So this is the one that's a finer time scale. This is the one that's coarser, and you can kind of see what I'm talking about. If you look at these longer stretches here where it looks like we have multiple interpolated locations in between detections, obviously these 2 are pretty autocorrelated, right? Same with these ones are pretty autocorrelated. These ones are pretty autocorrelated. But if you look over here, that autocorrelation looks like it might be reduced a little bit. So these ones are kind of autocorrelated, but it's just a lot more variation in those step lengths, you can tell. So blast through this, prep it, fit it, plot it. Still waiting for it to plot. Yeah. Okay, so. Yeah, so if you look at this, if you look at that bottom left plot, you can see that the autocorrelation function has reduced a little bit. So this is the original model. See how we have these like longer, we have autocorrelation that's lasting for quite a bit longer. You can tell it's reduced a little bit here. So that suggests that autocorrelation can also be a factor of just the linear interpretation, or linear interpolation. So you can try different starting values, run through this. So now here, yeah. So here, I'm trying different starting values. Looking, we have the same parameter values. So in this case, didn't have a super bumpy likelihood. And I think for these for these ones, I just randomly selected the starting values from something relatively reasonable. So that leaves us with one other option, which is accounting for autocorrelation using MarkMod Mover. And so this one inherently calculates it within the movement process itself. So this is not something that you can do in Move HMM. I'm going to blast through this a little bit, but MarkMod Mover uses S4 classes. If you want to learn about object-oriented programming in R, you can look here. But basically, for some of it, instead of using the $sign, you have to use an @ sign, or you can use a retrieval function. Ethan has a really good vignette here. Basically followed this for the analysis. But it's kind of the same formulation. So you have a user-supplied data frame. You create an object that can be read by the model. That's called data, that using the data4m function. Then you fit it, and then you can do things like plotting residuals and simulating to see how good your model actually is. First thing that we need to do, though, is actually unproject our data. So a big difference between MarkModMover and MoveHMM is that MoveHMM you can use both either latlon or UTM, but for MarkModMover you can only use latlon. So I just we already covered this a little bit, so I'm just changing my projection here. Or here I'm creating a spatial point data frame with the correct projection to tell what kind of projection it's in, and I'm transforming it. It's back to latlon, and then just double checking that everything worked. So plotting the world, checking out where we are, and we should pop up in Denmark. And here we are. So that's good, so it worked. So now what we can do is use the data4m function to prep these data. And it has a bit of flexibility in the naming of the data. So I just renamed everything lon and lat. Lon and lat. But I had to here rename top to date, or add it. So you can take a look. This gives you a bunch of different information about the track. So we can look at the length of the track. We can look at the date range, spatial range. This is really important. It's the time differences. We already kind of knew this, though, because we looked at it before. But your mean is 0.025, which is 90 seconds. So this is done in hours. This part is important, too. So MarkModMover will do the interpolation for you. You just need to tell it how and tell it when. So it hasn't been done yet here. But that's what we're going to do next. You have to parameterize it in terms of the hours. So take 90 divided by 3600. That was 90 was a previous time step. You get 0.025. No surprise there. Interpolate it, print it out again. Okay. So now the interpolated locations have some summary info on them. So we put in a good time step that gave us about as many locations out as we put in, right? So we have one less. So good on us. Contiguous groups, this is a way of splitting up your data tracks when you do have those data gaps. MarkModMover will actually split it up for you, which is really nice. And I have a little bit more notes on that, and I have some examples later on, I think. I do. And it tells you the time step, and it tells you the group cutoff, which helps you decide how many groups you should split it up into. If we plot the new data, first of all, we take a look at the structure. This is just showing you the S4 structure. So again, we have to use @ signs instead of the $ signs sometimes. So I just like to look there. Plot the observed locations, interpolated. Check it's okay, looks okay. And then we want to use the actual MarkModMover function to plot the pike. So first we have the interpolated locations, and then we have a couple of other graphs. It's a little hard to see these, and that's just because we have some outliers here. So down here, what I do is I clone the data. First I look at those outliers. So you can use the function boxPlotStats. So here I'm selecting out the step lengths from the interpolated data, and then looking at boxPlotStats. So we have a fair number of outliers that are out there that are kind of skewing this graph, so it's just hard to see. So I just clone this real quick. And then what I'm doing is just filtering them out, taking anything that's less than 2, just so that I can get a zoom-in picture of the plot, just to get an idea of this and show you guys. So and still, once you get the plot, it doesn't really work. Hang on. Oh, well. Oh, there it is. Okay, so these plots here rush through this now. There we go. Yeah, that's a good point. Fine. Okay, so these plots here, this one here is really important. It shows you the step length autocorrelation, basically. So this is your step length at time t, this is your step length at time t minus 1, and then this is a two-dimensional kernel distribution. That's just smoothing through that. So if we have basically a contiguous line along y is equal to x, that means that there's a lot of autocorrelation in our step length that needs to be accounted for. If you have these kind of like droplets along it, like this, then you could probably just use something without autocorrelation. And there's a couple more notes in there. This one is just showing you basically your track, but in this, it's kind of like taking every movement vector, putting it back on the 0, 0 point, and then showing you how the animal moved. So this direction here is straight ahead, this direction is behind, and then the distance away from the origin is your distance of your track. So we see that we have quite a few steps going ahead, and they're traveling far when they're going that way, right? It's just showing you an estimate of the different kinds of states. In order to fit this model, we just use the fit function, so it's going to randomly select your starting values. You don't have to worry about that in this one. This one's using TMB too, so we just got a good little intro to that. It's new. I think that's just a plotting thing. Okay, that was just a plotting thing. Take a look at the information that comes out. We start off, we have all of the previous information we knew. Then we look at the model definition. So here we pick two states again. HMM equals false, so you can actually fit a model without autocorrelation, and that's what this means. So if this says false, then you're not using autocorrelation. If it says true, then you are. Tells you the gamma the distribution that you decided on for the step length. You can also incorporate zero inflation, angle zero inflation. This is important. It tells you the convergence of your model. So same way that we were looking at convergence codes with Henrik's stuff, we need to look at this too. So you want a code that either says 3, 4, or 5. You don't want anything else. You definitely don't want 8. 8's bad. It's false convergence. Down here, we have the step length parameter estimates. It's your mean reversion level, so this tells you the average step length that you're going to take without autocorrelation, basically. And then your autocorrelation is added to that because you're saying that your next step is related to your previous step. So that previous step actually gets added to your mean. And then you have your standard deviation. Then you have a transition probability matrix here as well. So again, just like with move HMM, we have these higher values within the diagonals. And then in this case, we actually estimate the stationary distribution always. So we have a 0.65 probability of being in state 1 and 0.34 probability of being in state 2. In this case here, we're looking at the higher step lengths are going to be in state 2. We can see because we have a higher reversion level and a higher autocorrelation. So the larger step lengths are state 2, so that traveling behavior is actually in state 2. And then the residency behavior is in state 1. So the state definitions have actually switched from the previous one, I think. We can get the states using the Viterbi path function. And then we can look at this again. Look at these plots again. Yeah, similar interpretation. Okay, now we take a look at the model diagnostics. And that'll be all that we'll have time for. So, first plot that you get out is just your original data. It says satellite locations here because it was used for Grayscale GPS stuff. Second plot that you get out is your interpolated locations. So these are the ones that Mark Monmover did for you. And it's also got the states encoded here. So here we have these residency behavior in state 1. And then in state 2 we have that traveling behavior. And then we get these plots again, which are hard to interpret right now just because we can't see, but we saw them before. And then finally, we get different model diagnostics. And so here what we're looking at is, these are, again, autocorrelation and residuals, but a two-dimensional plot. You have your QQ plots, and you have a one-dimensional autocorrelation. So it looks like we have less autocorrelation now, but it definitely looks like there's something else there. And this should look like random scatter. It does not look like random scatter. So there's something else going on here. And basically what I ended up doing with this, let's see, Yeah, so here we can compare the two different models. So we see that the ACF is significantly reduced, which is nice. But there's still something going on there. That's indicative, in many cases, of potentially, when your model fit isn't good, you're clearly not capturing some kind of structure in the model. Okay, so that's one way of thinking, okay, maybe I need a third state. And so that's what I ended up doing. And you can read through all this. I really tried to comment it a lot. And so, this part, except for this part, but these are just different QQ plots. So I really tried to comment it a lot in terms of the decisions that I would make. And so I kind of show how picking between behavioral states is a trade-off between the biology of the animal and interpreting those different states, but also things like your model fit, right? And your things like your AIC. Be careful with the AIC. Lots of people talk about how I think it's suggested that it favors more states regardless. Down here, we also look at, let's see. What do I look at in here? Here I look at picking so here I demonstrate that. I just fit the model multiple times. And here, oh my goodness. Fit the model multiple times here here we go. Here I fit the model multiple times, and with multiple different behavioral states increasing it. As you increase it too in Mark-Bond Mover, you'll see that you get convergence problems. Those ones you need to throw out. And so those ones, if you're getting convergence problems or problems with your residuals, then you're not going to want to use those models. And so throw those out. Then you can compare and look at all of the different residuals and residual diagnostics. And when it kind of starts to taper off and it doesn't look like you're improving your fit at all in terms of your residuals, then you can also think about ditching those models too. But your AIC might still improve even though you're doing that. And so again, it really comes down to being able to interpret the biology of the animal. Let's see, what else do we do? Here I show in lesson 4. Here in MoveHMM, you can actually fit these to multiple animals. So what you do is you assume that 2 different animals or 3 different animals or however many have the same movement characteristics, right? So 2 different pike in the same lake are probably going to move the same. They might not be using the same habitat, but they might be moving in the same way. And so you assume those, and then you estimate those parameters across those multiple animals. And so you can do that with MoveHMM. The machinery is there to do it in Mark-Bond Mover as well, because that's how Ethan deals with data gaps, basically temporal gaps. I don't think it's functionally available, but you could hack it for sure, or we could hack it. So we do that, and then finally, in the last example I have here, the last lesson, we fit to seemingly messier data, and that's using this positioning data from Telma Pinpoint, and that gets really, really tricky. And I can only do it for a certain subset of one data set. And it goes to show that it can be really hard, and when you can't fit a model to data, it means that something's not there. And it's likely leading to NAs basically in your likelihood evaluation, because the model or the data are saying this model is not correct. So I tried to comment these out. Feel free to ask me any questions that you might have later, because we're 3 minutes over time. Thank you all for a fantastic day. I think we had so many good lectures and lots of knowledge transfer. I think in retrospective, maybe I would rearrange it so that the more complicated ones aren't at the end of a super long coding day. But I hope you guys all took quite a bit out of this. I know I did. And so with that, I think we're going to end for the day, and we'll reconvene at the Good Robot for 6:30. Food is coming out. So 6:30, we can get to the Good Robot. You guys are each going to get to order your own meal. So get there at 6:30. There will be appetizers waiting, and then you get to pick something from the menu. And so we order that. Panel starts at 7, and then panel will probably last 40 minutes. You'll get your meal, then we get to eat. 45 minutes. Robert's in charge of the timing. All right. Thank you all so much.